Hey, this is Horner, and we're going to go through magnets and magnetic fields. We'll take a look at that. We'll also look at some magnetic forces. So magnets cause a particle in space to be modified, and that actually creates what we call magnet fields. So magnetic fields, electric fields, they're both fields. We've also looked at gravitational fields, but magnetic fields are a little bit different. They don't behave like your fields that you saw from electricity and from gravity. Instead, they are a little bit different. So the magnetic field is very similar to the poles. If you think about electric poles or charges, that's very similar. And here we've got a north pole on a magnet. That's where all the lines leave the magnet, and the south pole is where all those lines re-enter. So I'll show you a picture of that here in a second. They also differ from electric field lines because they're continuous loops and they don't have really any beginning or end. When we think about electric fields, we usually think about moving from one spot to the other, from high potential to low potential. So this is a good example of a magnetic field. We'll see that it's starting from the from the north end, and then it curves down and around and comes back into the south end again. So you'll kind of see this as it goes through. We'll talk about magnetic field direction in that. This is a picture that they took. They have a magnet, and above it they put a piece of glass, and then they put iron filings down. So iron shavings, and then you can really see that field very well from those. A little bit more about magnetic fields. The Earth is interesting because the North Pole of the Earth is actually the North geographic pole is the South magnetic pole. And so this picture is actually incorrect. So I pulled this off the web. This is why you have to be very careful. This is actually the south magnetic pole of the Earth, and you'll see they even have an S there. I think it was just a typo when the publisher went through and did it. But the south magnetic pole of the Earth is where the north geographic pole is, and then that way your compass always points toward the north geographic pole because this is the north end of the magnet and the compass. And so if we think about compasses, compasses are actually just little magnets. And so if they're allowed to select their own orientation, these magnets align. So the North Pole points in the direction of the magnetic field, but it points towards the south magnetic pole of the Earth. They're really just magnets. They can easily rotate and align themselves in the magnetic field. And the North Pole of the compass points in the direction of that magnetic field itself. So it actually points toward that south magnetic pole. Here's a good sample problem. This one just says a compass points towards the Earth's north magnetic pole, which is near the North Pole. If the north magnetic pole is the north magnetic pole of the North Pole of the Earth's uh, magnetic field, and no, it is not. It is actually the south. So we said that this really should be south. And there's a link here that if you want to go to it, you can actually kind of see how that works. It's pretty cool. So we'll pull that link up. And here in just a second, it should come back up. So we'll pause this for a second. And so this is the website. This is looking at the universe, and they show you the Earth, and you can kind of see how it goes from the north magnetic pole back around to the south magnetic pole of the Earth. So the north magnetic pole is at the bottom, and then the south magnetic pole is up at the top. So we're always moving from north to south. It also shows you some other things. So if you ever want to get on that and take a look, it's really kind of a cool little website that'll do that. Magnetic monopoles. So is there any way that magnetic fields can have just one pole? So we could either have just a north pole or a south pole. And no, there is not. Magnetic poles can't be separated. If you take a magnet and, for example, you cut that magnet in half, where you used to have a north and a south pole, if you cut it in half and separate it, you'll have a new north and south pole. And that's different than what we did with charges. So charges, we actually, if you had a pole and then you had positive and negative charges on it, they're scattered throughout. We also, if you remember, could have objects where if you polarize this and you made it so that it's positive on one side and negative on the other, for example, you might put a positive sphere over on this side. And then if you cut this thing very quickly, this side would be positive and this side would be negative. So this would all be positive, this would all be negative. You can't do that with a magnet. Every time you cut it, you get a new magnet that has a north and a south. You just get smaller and smaller magnets as you go through. So there's no such thing as a magnetic monopole. The units of magnetic field are Teslas, that is a Newton per Coulomb times a meter per second, or a Newton over an amp meter. And we will use that Tesla most of the time. Another unit of magnetic field is called a Gauss, and 1 Tesla is about 104 Gauss. So on the next one, this one just talks about the magnetic force on particles. Magnetic fields do cause the existence of magnetic forces. And so anytime you have a magnetic force, it's exerted on a particle within a magnetic field only if that particle has a charge. So whatever it is that's affected by the magnet, that thing has to have a charge. And that charged particle is going to move with the least of its proportion of its velocity, should be perpendicular to the magnetic field. So if you have a magnetic field, and we abbreviate that with a B, the particle cannot be moving along the magnetic field. So if your particle is moving this way, it's totally parallel. It's got to be moving perpendicular, either completely perpendicular or have a little bit of velocity moving perpendicular in order for it to be affected by that field. I make it kind of similar to, if you think about if you were to walk through traffic, if you start here, or better yet, if you start here and you walk along with traffic, you probably won't get hit. If you start here and you go across, then that field of cars would take you and push you. So that's what the magnetic field tends to do to particles, makes them turn. The magnetic field force on a charged particle, there's an equation that goes with this, and that force is equal to Q, which you already know, that's charge in coulombs, times the speed in meters per second, times that magnetic field that we talked about earlier. And so we use B for that magnetic field. And then we need to do the sine of the angle. The direction, you have to use the right-hand rule. So we'll talk a little bit more about the right-hand rule in class, but it's a pretty simple thing to do. We'll illustrate it here in the PowerPoint and then really go through it in class. And we can also make this equation F is equal to Q times the vector V times the vector B. So we could do a vector cross product, and that is how we're going to use the right-hand rule to help us figure out the direction of that magnetic field. So magnetic field typically will abbreviate with an F and then a little b, since B is the sign for a magnetic field. This is the right-hand rule. There's a couple of different ways you can do this. We can align our hand along the first vector. We orient our wrist so that you can cross your hand into the second vector. Your thumb gives you the direction of the third vector. So that's one way to do it. I really like the one here that gives us the force. So we're going to use either, if we have current, that'll be our index finger, or velocity. So sometimes what I have people do is actually take a pen and write V on that finger. On the middle finger, they'll write B, and then they'll write F on their thumb. And notice that this is called the right hand rule. If you use your left hand, this does not work. So we want to make sure that we use the right hand rule to determine this vector cross product. So I'll help you with that in class a little bit. First sample problem says they want us to calculate the magnitude of a force exerted on a 3 microcoulomb charge moving at 300,000 meters per second in a field of 200 millitesla. And so the first thing we probably need to do here is go ahead and take that 200 millitesla, which is 200 times 10 to the negative third Tesla, and just convert it. So there we go. Now we've done the conversion. That is B. 3 microcoulombs is going to be our Q. So Q here is 3 times 10 to the negative 6 coulombs. And then here we already have meters. So we're set with the speed. So for letter A, it says if the field is directed north, the charge is moving north. So remember what we said, if our magnetic field is moving north, so here's our B field, and I have a particle that's moving north, it will experience no force. Same thing if the particle is moving south, it's not going to interact with the cars driving down the road, so that will also be 0. For letter C, now it's moving east. So let's do this. Let's go ahead, and the field is directed towards the east. So we're going to go this way. When we think about our axes, we're going to think about north, south, east, and west. So north is up, south is down, New York is east, and we know California is west. So that's what you'll see. Now, this is the magnetic field, so it's B. We know that that is the field. We know our charge is moving towards the north, And so that is the velocity of our charge. So if you take, and remember we said that you will put your index finger, so I'm going to put index here, I-N-D-E-X. Your index finger goes in this direction, and then you also have your magnetic field. This is your middle finger. So I'm going to put M-I-D-D-L-E. And if you take your index finger and you put your middle finger up, then what happens is the field, okay, so the force, field is to the right, the particle's moving up, it will get pushed into the page. So to signify that, we're going to put an X. We put an X because if I have an arrow, so for example, if I have an arrow and it's got the little feathers on the back, if I am standing here looking at that arrow, so there I am, I look like a bird now, don't I? So anyway, there's the arrow. If I look and the arrow's going away from me, I see the flechettes or the feathers moving away. So that's what this one would look like. So index finger, if you point it straight up in the air, you turn your hand so that your middle finger then points to the right. Your thumb should be pointing away from you. So sometimes we'll also say that this is into the page. So that makes it pretty easy to do. For letter D, the thing that we switch here is we still have our velocity of our particle going in the upwards direction, going towards the north. We have going west now is that B field. So we take our index finger, so our index finger, so this is index, this is our middle finger. And if you put your index finger straight up, put your middle finger to the left, then your thumb will actually point out straight towards you. So to signify the force, the magnetic force, so that'd be FB, this was FB here. Notice you see a dot. So if I stand on the other side and I'm getting shot, so there's my Birdman again, this person is going to see the tip of the arrow coming at them. So that's what they do here. That's how you can know that it's coming out of the page. So this is coming out of the page. And that's how you tell the direction. So we'll practice this a little bit in class, but I wanted you to see how it works and just try to explain it to you. All right, so for the next one, this is another sample problem, and this one we have to go through and calculate the magnitude and direction of the magnetic force. So notice that this one actually has an angle to it. So we have 34 degrees with respect to the magnetic field. That's the angle between the speed of the particle and the direction of the magnetic field itself. So we'll use our same equation that we did before. We know that the force on this charge is equal to the charge times its velocity times the magnetic field times the sine of the angle. Since we have an angle here, we've got to use that. Our Q we know is 3 times 10 to the negative sixth. Our velocity is 300,000, so you could also put 3 times 10 to the sixth there. Oops, 3 times 10 to the fifth. And then our magnetic field is 200 times 10 to the negative third. And then finally we need to do the sine of 34. Make sure you are in degrees. So your calculator should be in DEG and not in RAD. Once we do that and we run through, we should end up with a force of 0.1 newtons. So we found the magnitude. That was pretty easy to do. Now we need to find the direction. So remember, the speed is always our index finger. The magnetic field, now even though it's at an angle, you can do that with your middle finger. So this is your middle finger. And if I take my index finger and go up to the left, middle finger down to the left, my thumb is going to point straight at me. So this particle will feel a force, magnetic force, that will point straight towards you, okay? Or it's coming at you, not going into the page, but coming out of the page. So that is your sample problem, and that's the end of the first section of notes. Next section we'll look at motion of a charged particle in a magnetic field.